we have a much firmer understanding of what the algorithm is doing, we can proceed to analyze a data set. The first step in any analysis is understanding your data set. The standard orange distribution comes with a handy sample data, and for the purposes of this demonstration, we will be using the zoo.tab file. Now, we need to understand what this data set looks like. Thankfully, Orange provides this handy data table widget, which will let us look at our data as displayed in a matrix. Opening this, we find what the basic format is. The column headers here are attribute labels, and then down below on rows are samples. Notice first of all that this is a heterogeneous data set. While most columns contain 1s and 0s corresponding to true-false, the legs contain 0 through 8 corresponding to the amount of legs on our organism. Far to the right we have our organism name, and we have a type, which is already one type of classification here. We can use this to compare how well our hierarchical data clustering compares to what we intuitively clustered these organisms as later on. As mentioned earlier, hierarchical clustering employs a measure of cluster distances. Orange provides a nifty tool for converting this data matrix into a distance matrix. The details of this widget here can be explored elsewhere, but for our purposes, it creates an n-by-n matrix of distances between data points. Orange's hierarchical clustering widget can then pick up the nearest points, merge them, and calculate a new distance between the cluster and others based on some distance metric we will provide. We need to choose the example distance matrix. If we chose the attribute distance matrix, we would calculate the distances based on our respective attributes, hair, milk, venomous, etc., and not on our intended organisms. Upon clicking the example distance, we can see that we have several metrics to choose from. In this case, both the Pearson correlation and Spearman rank correlation are irrelevant to us. Instead, the Euclidean distance, Manhattan distance, Hamming, and relief will be most relevant. The Euclidean distance we understand to be the distance as calculated by the Pythagorean theorem. The Manhattan distance is especially relevant in dynamic programming. It calculates the distance as one would on a grid, the sum of the horizontal and vertical distances required to reach an endpoint. Hamming distance compares strings or sequences. It finds the number of substitutions required to convert one string into another. Relief here is a stronger version of the Manhattan distance. It relies on some underlying probability distributions to correctly provide a distance. For the purposes of this demonstration, we will be using Euclidean because of its intuitive nature to understand. The matrix is automatically sent down the pipe to the clustering widget, where we can interrogate it in further detail on the next summary.